Welcome to another wonderful episode of the New York City Category Theory Seminar. This week we have the honor and privilege of having Professor Sergei Artemov talking about consistency of piano arithmetic is a serial property and it is provable in piano arithmetic. It's pretty... He's going to explain every word of that.
Absolutely, and though it was announced as a dress rehearsal of my talk in almost a week and 5 days in New Mexico for a ASL meeting.
Went down to New Mexico?
Yes, it's an ASL meeting. I have a big talk there.
Yes.
On the thing.
Wonderful. Okay.
And so the thing is properly published. It's not, crazy fantasies or something and refereed, and that's pretty harsh and serious refereeing, yes. And there are many ways, many good ways now to start the story, but when I look at Nosson and his presentation, I recall that after my first big, my first talk about this matters was there at the seminar.
I know, it's on
And I was naive. I try to explain why things really the way they are. I try to speak my heart to what I understand, and immediately I was squashed by from different directions. In particular, there was some the professor in philosophy who said that before you speak about Hilbert program, you have to define what finitistic means. The end of story, because nobody did it. Hilbert himself, including it. It was better just go do jogging, so something. Just don't bother doing the thing. And now, and this was 19th, I guess, or 20, early 20s, so 5 years ago, roughly. And since then, the math doesn't change, though there are a lot of nice and juicy discoveries made around it, not only by myself, but also by some other people, and Willard was one of them, by the way. Yes, and but most importantly, the pitch, the way to present things, the all unnecessary decorations, bells and whistles, they disappear. Now it's just bare truth. But as a result, the message itself is rather short for the literate audience, but we'll have enough time to discuss things and answer questions. And the second thing, so after I gave the first really public talk, it's still on this super seminar on logic, and it was in Indiana seminar, and then Mike Dunn at the moment, he was alive, he was excited about the whole thing, and then it's still on the web, you can check it, and he said that once Raymond Smalian calls me and says, Mike, have you seen today's New York Times? I said, no, what's? Somebody proved piano arithmetic consistent.
That made it into the New York Times?
Wait.
Okay.
And the question is, well, in piano arithmetic, of course, that's the point. And April 1st Fools. It was. But at the moment, it was shortly after the talk, which gave a real mathematical proof of consistency of piano in piano. It was a nice joke.
Yeah.
Yes. Now, from two distinguished persons who are on the other side of the divide. So it was a kind of a very touchy message.
So this seminar may wind up in tomorrow's headlines.
Well, maybe we were talking about the 60s and the 70s. Things change, and the priorities change, the interests change. And I remember there are a couple of, one of them is Harvey Friedman, who say that he sold something, he did something in set theory, and said that if I would do it 50 years ago, I would be just the king of the hill. But now nobody seems to be truly interested. So it's not the case here because it's still in important. We touch in important things. Like changing some key phrases in the Encyclopedia Britannica, because it was not supported by mathematical research. Anyway, so thank you. So we mentioned the role which category theory seminar played in the whole thing, and so and speaking about big guys, yes, I'm sorry. The big mathematicians. On my side of the divide, I can mention Kolmogorov, who was my mentor at Moscow University, and Yuri Manin, who was a very good friend. Yes, both are. Perfect. But they both respected what mathematical logic does, very much. So that's why on whatever name you didn't mention, on the one side who was skeptical about things, I give you two cards of at least the same nomination, probably even more.
I think Manin wrote a book.
Exactly.
Well,
that's why.
Certainly.
Discovered things. Of course. Yes. Yes. So we agree that piano arithmetic, PA stands for piano arithmetic. Good. So why PA? Why piano arithmetic is just the iconic case when the impossibility of what I promise was assumed and just widely believed. First of all, before we do something, I'll answer an obvious question. What's the point of proving a consistency of a theory inside the theory? What do we gain? Because if the theory is inconsistent, then it will be able to prove its own consistency. So the yield of the proof of consistency of T inside T is 0. Mathematically, yes. Then we parse a little bit of what piano proving consists of PA and PA means, and we remember that Hilbert's approach was to prove mathematically the consistency of formal theory T, and then trying to formalize this proof in some other theory, just to tame the tools. But there are two stages, both are necessary to answer this question. So it means that we have two copies of PA. Now we're back to what is real PA. So there is a formal theory of PA, is just a set of symbols played by certain rules, formulas, some proof system, so the axioms, like the usual recursive axioms for plus and times, a successor, and induction scheme. But also it's a formal replica of something which is a real mathematical theory. This so-called, sometimes identified as elementary arithmetic. So you argue about natural numbers using only recursive definitions of plus, times, and successor, and induction as a scheme for any individual property you want to deal with. So this is a well-respected mathematical informal theory, which we called it contential. We'll use this word. And we separated and used the PA hat as a contential theory.
Do you have other examples of a theory? Is there a theory of groups and a potential theory of groups or something like that?
Well, of course, yes. It's the group.
Presburger arithmetic. Is there another Presburger arithmetic with a hat on top of it?
Of course. It means that you reason informally. You're not obliged to formalize it, to write it as a long lambda term or as something completely formal.
Putting the hat on it just means I'm going to use this as my meta theory, which I obviously don't formalize, so I don't get.
But yes, but if you're careful, if you're if you're reasonably careful, and you argue inside the theory, then this is a very widely accepted and empirical, like Church thesis. Thesis that if you do this in formal reasoning, you can every logical step you can formalize.
But I guess the important part is I want to keep the theory without the hat and that separate, you know, they're copies of each other just to keep things logical.
To keep things logically different because they play a different role.
Yeah.
But also, I will give you a good example, immediate example, which I know Professor Nosson would love to hear immediately. Why does this, how this distinction actually matters? And there are two-stage approach. It fits nicely the Hilbert idea. You do the mathematical proof and then you try to squeeze it to do it inside certain theory. And that's the point. There is, I considered writing a slide on this, but I didn't. So, yes?
One quick question. Why should we trust that trusted means?
No, trusted means it's just a matter of speech. No. Why do you trust it? We ended up with this one, of course. Trust no one, yes, of course not.
That's why it's in quotes.
Yeah, that's why it's quotes. Trusted means it's something which plays the role of trusted means.
Can I just say, I follow Edward Nelson, who believes that piano arithmetic is inconsistent anyway, so you can prove it all you want.
But he had a proof.
It's the easy way out. You're taking the wrong pill, and then you live happily ever after. Yes, of course, yes.
And then you start a foundation to form a code.
It's not a religion, really.
Look, I'm not sure that I didn't put it on slide because I was not sure that the audience know this. Do you know, are you familiar with Rosser proof predicate? Some do. It basically says that, whereas the standard proof predicate says, it says two numerical inputs. It says that X is a code of a proof of a formally having code Y, so it's X and Y. Device barrier. The Rosser predicate, it's corrected the whole thing. It says that X is accepted as a proof of Y if there is no earlier proof in terms of the value of X of not Y, negation of Y. Looks like an innocent modification. Looks like innocent modification because if you...
So make it consistent to consistent. Sorry.
You know too much. Now, let's build the consistency predicate based on the Rosser proof predicate, the consistency formula based on the Rosser proof predicate. Folsom is not Rosser provable. Here's a proof, the formal proof inside piano arithmetic of Rosser consistency. So if you just do this dual thing, dual dance with the quantifier, and the implication, it says that for all X, either X is not a proof of 0 equals 1, or there is an earlier proof of negation of 0 equals 1. So here's a proof of this thing in piano arithmetic. You find the shortest proof of not 0 equals 1. The 0 is not equal to 1. It's basically 3-5 lines. If you're unlucky, it's 10 lines. And you make sure that there is no earlier proof of 0 equals 1. There are just five just finitely many proofs that you can easily check that there are no standard, no models involved, nothing. And then you take an arbitrary X. If it's greater than this, if it's under this particular threshold, then it has been checked by manually. It is not a proof of 0 equals 1. If it's more than that, then the answer is yes, because there is, the answer is no, it doesn't qualify because there is an earlier proof of negation of the whole thing. It doesn't qualify as a proof of 0 is not equal to 1. So the consistency formula based on Rosser proof predicate is provable in piano arithmetic. Why are we not accepting this as the proving consistency of PA and PA? Use this filter. It should be a real proof of consistency, and it is not. It is not what I said. It's a formally proof of that 0 equals 1 is not derivable in well. It's a formal derivation of a proof of a that X is not Rosser proof of 0 equals 1. However, the mathematical substance of this argument is that it says that even if it happened to be proof, I just have some creepy way around to formally satisfy this, but it does not yield the real proof of consistency. And every sane mathematician immediately sees this. It is not a proof of consistency. That's why if you just do this very naive filter, we filter out some garbage. And this is an answer. I know some of the people who really believed in Rosser proof predicate and who really believed in Rosser consistency and also try to argue that maybe that's the way we should treat consistency now. Proof theoretically, if you look to take the consistency formula and Rosser consistency, proof predicate and Rosser proof predicate, they're equivalent only if you assume that PA is consistent, which makes it useless in analyzing piano consistency. So there are different entities, and they're equivalent, but of course if you assume everything, if you assume inconsistency, then everything becomes equivalent. It's not the point. You have to see the equivalence within the given boundaries, formal boundaries, like PI, and there are PI different. They're not equivalent to piano arithmetic. And this is the trick, the explanation of the trick. Now, so we agree to this. There is some Gödelization. There is some rather fuss, but also, yeah. And we try to be careful because the whole business, it's full of traps. The whole theory, and I know serious people who really just stepped on them and were not easy to free themselves out. So let's try to be a little bit more careful. In notations, n bar is a numeral, 0. It's like, remember the wonderful talk by Artemov about what's the natural number, and the Hilbertian bars. The Cermello.
You're trying within your piano, I assume.
And this is a piano. It's just piano term.
0.
It's a piano 0 within strokes, successors. And this angle, the corners is a Goedel number of X, and we don't want to be completely always pedantic because sometimes we don't need this. But so when safe, we do not distinguish the syntactic object, its Goedel number, and the corresponding numeral. But deep in mind, we have to realize that there is a difference, and sometimes it matters.
Well, there are different types of things, so...
Good. In category, different types of things. Absolutely true. But they're abuse the names, of course. The usual story. The standard definition of PA consistency, informal. We're not speaking about the formula or whatever kind of. It's just a mathematical fact. For any derivation, or if you wish, correct my rudimentary English. I will say that for any derivation, for all derivations, for each derivation, whatever. But mathematically, I hope that we understand each other. Yes. For any derivation G is not a proof of 0 equals 1. Here I allow myself putting some bars over line bars because this is really formula, and the formula means a term, and here's a term, and this all is correct here. Derivation is a finite syntactic object, X, which has Goedel number and the corresponding numeral. And the proof predicate x colon y, I'll be using it many times, and that's why writing beweis bar or proof xy is just too muddy. So colon x colon is natural primitive recursive arithmetical formula. X is a code of a proof of a formula having code y. The standard things. And Eli taught me that here it's a time. It's a moment to mention that we're speaking about specific fixed proof predicate, but of course it works for the whole range of it. We just don't bother circumventing. Yes.
Not using the Rosser trick or using...
No tricks, no. Straightforward, and moreover, this is a primitive recursive thing, so basically it's a primitive recursive term. When you just calculate this term and it says 0 when it's true and 1 that is not, or otherwise, and that's it. So it's a formula, but the trick is that this formula is written having the specific proof-checking algorithm in mind. Honestly, of course, and no tricks to fool people, and that's why it's safe to counter the Gödelization. Well, this is a combinatorial statement about finite strings, about finite words. And this is about natural numbers, and that's the first moment when you can lose some of the audience. You say integers, but it's not just about integers in some abstract sense. It's about numerals, because the Gödel code of derivation is a numeral. There's a trap number one. We say, well, it's a natural number. What do you mean natural number? Are you with?
Excuse me.
I'm guilty as charged too. So I'm not in Carnegie Hall, so I didn't have this. No.
I always have it off. Excuse me.
So what's a natural number?
Just to be clear, 1 and 2 are in PA hat. 3 is a set.
Yes. I'm still there. It's not even in PA hat.
It's in English.
It's in English. This is in PA hat. And this is a set in PA. Mm-hmm. But set is, in PA, there are plenty of things about sets in mathematics. For, I don't know, deduction theorem. Plenty of things.
So, okay, for any numeral that's a phrase, well, that's...
For a numeral informal, it's informal quantifier, which is not directly expressible in piano, and we know that piano cannot specify numerals or, well, standard model is not definable inside piano arithmetic. That's why we can compare this one and this one. They're actually identical, because one of them is just the Gödelization of the primitive recursive.
Just to be clear, I mean, if I take any natural number, the way I've numbered my derivations, every natural number will be a derivation. Correspond number a derivation.
Well, if you care about filling the voids in the thing, so if you do this the straightforward Gödel numbering, there are plenty of garbage in there.
No, that's what
but you say but since things are decidable, if there's a garbage, I'll output some trivial derivation.
I see. So it can recognize the garbage, and if it's not a garbage number, then it's...
Yeah, absolutely. Yes. So with this technical proviso, these things are just for each derivation there is a number, and for each numeral, and for each numeral there is a derivation.
Right, but the point is a number can only refer to a derivation or be an ill-formed formula that's not a derivation.
But you can, since you do the mapping, when you do the mapping, you see, you consider there's one simple derivation who has very many numbers. And The important thing is, however, that they're well-defined mathematical statements. There is no... mathematicians understand what 1 and 2 means. Moreover, 1 and 2, they're obviously equivalent, modulo to this technical assumptions about numerations. But the problem is that none of them is in language of piano arithmetic. And to ask the question whether 1 or 2 is derivable in piano arithmetic is just a different language. They don't understand it. Sorry, you have to make one more step. And to make things short, I give you the answer, and then we compare it with other things. Because when I was in the first moment, I'll spend 5 slides trying different things, and I ended up, that's the one. I give you the one. Now I know that we'll never end the story, because we'll begin discussing totally irrelevant things. So this consists of scheme. And on the next slide, you'll see that all 3 are equivalent, and there is a very good role this consistent scheme plays. There are 2 ways to read this CONAS, this consistent scheme.
How can you say 2 things are consistent when they're not in the same language? Or they're equivalent if they're not in the same language?
That's exactly what I try to explain why. With this one, we agree that these things are mathematical statements and they are mathematically equivalent. This scheme is of dual character. It is a well-understood mathematical statement, because without quantifiers, the column itself is a very well-defined primitive recursive claim. The instance of a primitive recursive predicate, which is very well-defined. But it happened to be in the language of formal arithmetic as well. Of course, if you believe in Gödelization, but no reasons to. If everybody can write this small program which is doing this, you just repeat the definition of derivation in terms of numbers, and you'll get this column. So, very good question, and this is the key role this particular schema 3 plays. It's the breach between the contential, the consistent property in piano arithmetic.
While you're drinking, I just want to say, about 2,500 years ago, a man named Zeno lived, and he basically said that the universe doesn't work well. He said the universe doesn't follow the real numbers, because in the real numbers I can prove that I can't move. Okay, and which is true, by the way. You can't do a finite process. You can't do a stroke, whatever. But obviously, I can move.
Yes.
So the language that we use,
yes,
assumes the real numbers, and we make every physicist take a lot of classes on real analysis and things like that, but we don't really follow that.
This is, well, thank you for this reminder. It reminds me why I'm in discrete math rather than in continuous math, because I understand the strokes, but I don't quite understand this, the infinite or the Dedekind cuts. They're fine.
Well, don't worry, that'll be next week's seminar.
Good.
He's serious, because he's speaking next week about this problem that we have with calculus, namely when you say epsilon is a small number, but epsilon squared is equal to 0. That's...
No, I understand. I understand. Well, physicists also, this Dirac function, it's a very good example also.
We have a question.
Yes.
Yes, so I have no question that the 3 is an expressible statement in PA, in the language of PA.
Yes.
If this column is expressible in PA, do we have a simple argument that there's a column that we define using Goedelization is expressible in PA?
This is one of the previous lines. X colon y is a natural primitive recursive arithmetical formula. Of course it's expressible, because all primitive recursive conditions are expressible when more or less natural way, but there is one, you just write it down as a primitive recursive term. And that's it. And of course, by the way, in arithmetic, we assume that there are terms for all primitive recursive functions, along with their recursive definitions. So we can, in the axiom scheme extended to this language. So we can, or we can do this the Goedelian discovery that you can represent a primitive recursive thing with a formula. But for convenience and in the functional programming tradition, we just use terms. But it's the same thing, of course. So good point, because it's when we clean in the first 3 slides, then the rest is a breeze. So we're slowly moving through the most difficult terrain. There are almost no tricks left.
So the bottom line is that 3 consists of well-defined statements or well-defined theorems?
No, they're statements. The theorem and then the next slide. Because it's...
I mean, it's provable that 0 doesn't prove whatever. That can be done.
It will be an important ingredient in our future, the proof that arithmetic is consistent indeed. But we have to just be careful what comes first.
If you assume these are theorems, then there's nothing for you to prove. You already admit that the PA is consistent.
I never did this.
Right. So that's why I say we should call these statements. If you assume...
Oh, yeah, well, that's yeah. But because, and then, but Nossen, you're very right in a certain amount. You're both right. Both of your inputs are absolutely correct. At the end of the day, we prove all, in several slides, we really prove this thing in arithmetic, but this thing is not a formula. That's why the standard Hilbertian the standard definition of proof of a formula doesn't work, because what does it mean for an infinite set to be provable? We have to define it. And there are good hints how to do this, but this is one of the contributions of this work. We're developing the so-called selector proofs.
Right, each element of the set is a thing I can prove, Hilbert style, but the whole set is another story.
Yes, yeah, because that's, they'll be all good examples. You're asking good questions, but just bear with me a little bit longer. So now the thing. The proof of this equivalence is a formalizable in PA or standard Goedelization. So 1 and 2, it's just the Goedelization, which is just rewriting the whole thing. So basically what we do, if we concentrate on proving equivalence on 2 and 3, and yes. Okay, what is, how would, as a mathematician, how would you prove that 2 and 3 are equivalent? We'll say, okay, we'll take an arbitrary numeral and we'll find thing there. And so it means that, and then we're thinking about, if you try to formalize the whole thing, then there is no such a thing as variables for all terms for sets, but it's a well-defined sequence. Well, this easy primitive recursive numeration of this set. So we're not. That's how my not very numerous, but my opponents, they try to say that you're using the notion of a set, so it's set theory. Forget about it. Well, but what you're doing is you generalize the problem to unsolvable. Don't go to the whole, we don't need sets. We don't need big sets. We don't need sets at all. What we need is just numeration of one specific thing. And it's just primitive recursive. It's a primitive recursive f, which, given n, returns the Gödel number of the thing. So what we need is, if you want to speak in terms of to speak in terms of truth, or because here we speak in terms of truth, and here we return the number, and there's a very nice device, underestimated device. There is the so-called truth predicates, which convert a Goedel number of a formula into the formula provably in piano. But the one says, there, of course, by Tarski theorem, there is no universal formula, which the truth definition, which works for all formulas, but for complexity classes there are. In particular, it's sufficient to have to have the formula, to have the truth predicate for sigma 1 formulas, because all these phi's are simple. They are dealt.
Remind me what's the sigma 1 formula?
The existential quantifier.
Oh, okay.
One existential quantifier. These are all quantifier free. So there are sigma 0, delta, delta. So you just run this usual mathematical definition, and at the moment when you want to move from truth to Gödel number, because you're given, the thing is given as bench of Gödel numbers represented by a recursive function. And then, but you take this number, you take n, you recover the whole thing, you use truth predicate, you recover the formula of phi, whatever. That's it. And they're all provably equivalent to piano arithmetic.
Tarski's theorem says what? Is it a pi1 statement?
No. Tarski theorem says that there is no truth arithmetical formula. There is no truth which works for all phi's. But the desired equivalence is this one. And it's impossible for all phi's. But for phi's in this particular sequence, which are all limited, they're all primitive recursive. The truth for the easiest truth definition for sigma 1 sufficient. You can do truth definition for all n's.
Can I just go on the second sentence? It can be formalized in PA in the standard fashion. Finite objects, derivations, numerals are represented by Goedel numbers. Now, statements in PA, but number 2 is not a statement in PA. Number 2 is a statement in PA hat. So.
Oh yes, yeah.
So proofs in PA can be described by PA.
Yes.
But you're bringing in a new thing. 2 is not in PA. 2 is not a statement in PA.
Absolutely. That's why it is proposition. It's not just proposition, which says that we consider now remember dual character of the scheme. We consider a real mathematical equivalence of this in PA hat.
So you're saying number 3 really sits
in both.
In both.
Yes.
Now, number 2 sits only in.
That's why we need number 3, because it's a bridging to.
Okay, so the next slide basically says as follows. Piano arithmetic can deal with piano arithmetic.
Yes.
Piano arithmetic can also deal with PA hats. Because we deal, right? Because it's a finite thing. Piano.
Yes. And through Gödelization, absolutely yes. Okay. You can prove things in group theory and in arithmetic. Because finite group, blah, blah, something returns and subgroups things.
That's computable.
Yep, absolutely.
Okay,
but standard model is not.
Standard model?
Of piano arithmetic. It's not computable, so it's not a subject in PA. Anyway, so that's good.
But in order to do that, you're going to have to formalize PA hats.
No. It's sufficient for me. That's one of the reasons why Hilbert did not formalize the finitist, what finitism is. Because he believed that if he has a proof, it suffices for everyone to believe that this particular proof is finitistic, acceptable, blah, blah. There is no need to go to the clouds. And that's here. I don't need to formalize the whole PA. It's sufficient for me to formalize this particular proof that 2 is equivalent to 3. And this is a finite mathematical reasoning, and each step is completely standard. And there are completely standard ways to formalize it. No tricks, no Rosser tricks. Just modus ponens, corresponding primitive recursive operation. And
I just want to say, here's 3 wonderful people. He's going to say for all numerals n. He's going to say for each numeral n. And he's going to say for any numeral n. Okay? Those are 3 statements within PA hacks.
They're all mathematically equivalent, and they all survive this kind of formalization. Take your favorite reading, you end up proving that this thing is equivalent to this one. Because the scheme is very simple. And this was the essence of our morning discussion with Roman Kozak. He invoked a wonderful theorem, which says that about ranks of proofs and things and those things. He said, yes, but we take this. This is a very simple thing. When you end up, it will be just claim about instance probability of the thing, which was a well-known since Goedelian time, that each one of them, thank you for mentioning it, is of course true and provable. So this thing is so simple that many things which are different, in particular, they may be different there, they end up with the same thing in here. That's the beauty of mathematics, and that's why we're going to very simple mathematics. When all this, the color of pills no longer matter. It's just the bare truth. All right, but we already made the strongest. We can already go and finish the talk in pub. Yes.
So the title of this frame should read omega consistency of PA is inside of PA probably equivalent to consistency of PA, right? Is that your...
Well, there will be special slide about omega rule. Don't worry, we'll do it. Okay. You speak about omega consistency. Well, yeah, it's so well paved area. Then everybody crossed this piazza in all possible and impossible directions. And thus the cobblestone is completely polished. And you can go anywhere. You can this way, that way, this way. They'll all be right. But I want certain message to be delivered within the reasonable time for the talk. So let's continue. But you're right, yes. So, but the corollary, which is probably the strongest of the day, that PA consistency is adequately represented in the language by the consistency schema CONAS. 3 is a fair representation of consistency. Before you swallow this, let's do the consistency formula. Why this thing, beautiful thing, doesn't work? That's how I try to start this, my talk 5 years ago. So let's try to answer the fundamental question of whether con PA is like this consistency formula is equivalent to the property of PA consistency. Can such an equivalence be established by means of piano itself? Let me see what's next. Oh, yes. Okay. Just in order to go on. The truth is the consistency formula is not a well-defined mathematical statement before the domain X is specified. Because column, it's all right with the column, we understand what it is. But what is X? Well, moreover, what is for all X? Here's the natural argument, again, like it's a well-paved, well-polished piazza somewhere. Piazza San Marco, and so on. Includes salty water and all things, completely polished, yes. Okay, well, without loss of generality, we assume that Goedel number is surjective as we agreed. So each n is a code of some derivation. Suppose non-con PA Well, listen, I try to say that it yields consistency. Non-con PA, then for some standard n, n bar is a proof of falsum, hence for some g is a derivation of contradiction. Obvious gap in this reasoning. Because the negation not con PA doesn't yield that there's a standard n which does the job. So there's no derivation behind it. So the whole thing fails. So in order to this to be true, you have to assume that for all x range over what? Standard model. Then you assume standard model. The store is closed. It yields consistency. You're assuming consistency for proving consistency. So within, it means that within piano arithmetic, mathematical statement, consistency formula is not equivalent to consistency, and we'll show it immediately. So at least this argument, the natural argument, that's how I won some of the last battles with people. They say that there are some believers in con PA. Okay, prove me that con PA as a formula yields the consistency. Or just give me a mathematical proof that consistency as a property is equivalent to formula. They never return back. Because there's no such a thing, and it's clear why. This argument assumes that for all x range of standard natural numbers, not formalizable, the claim that the equivalence of a consistency of con PA has no justification in PA. Moreover, we can show that con PA is strictly stronger than PA consistency. When now we have a golden standard, which can be understood in piano arithmetic, which is con S, the scheme. Many reasons. So con PA is strictly stronger than con S. Logicians see it immediately because the universal quantifier is stronger than the set of instances. For example, it's easy to prove assuming con PA, it's easy to prove all the things. We don't actually need this one, but it's. When PA plus con SPA doesn't prove consistency because the thing can be ignored because they're all provable in there. So. Or model theoretically, if Roman would be here, say that con S is true in every model of arithmetic because it speaks only the standard part, and the standard part is always it's the same. Whereas this one fails in some non-standard models. So that's why the thing is strictly stronger than this one, model theoretically as well. And this is an obvious. So it means the unprovability of consistency thesis, there exists no consistency proof of a system that can be formalized in the system itself. Encyclopedia Britannica, wow. I believe it never been justified. It's, well, now we notice that it has not been justified because the unprovability, the Goedel theorem G2 doesn't, that claims that piano doesn't prove con PA, but it doesn't yield the unprovability of PA consistency because it's how philosophers like to say this is a strengthening fallacy. You prove that something stronger than you need is unprovable, and then you go to pub, saying that you can do nothing about it. Well, and this, the unprovability of consistency thesis appears to be one epic blunder in foundations. Surprisingly, some of the people try to play on this thing that for all n, or for every n, and for each n they're different. So I have to really just walk to do this mathematical frame, which eliminates the whole business. But this was a level of discussion of the general public. When you go to the general, like math overflow, there's FOM, it's dominated by non-professionals. it's very difficult to deal with them because they have their own funny ideas about how things are, how the world economics works, how the whole thing. Okay. But this, I try to make the story really straight. So, on SPA, that's the only PA acceptable definition or representation of consistency. It's a scheme. Unfortunately, it's infinite. It's an infinite scheme. It's not finite. And the proposition one. But the question is PA consistency really provable in piano? Then we have to answer this. That's the object we deal with. A serial property, the first step would be developing the rigorous notion of proof of a serial property. Fortunately, and such as that's a serious, yeah. Do we still have some time?
We have as much time as you want. What's
yes.
a serial property?
The serial property is, there is a definition.
You can prove the whole series, right, in PA.
That's exactly, the next several slides will be discussion. What is the proper definition of this? And examples, because there are plenty of serial properties which are already assumed, considered in piano and assumed to be provable, and then we'll see. This is an example of a serial property. It's just the infinite sequence of formulas. There are instances of the same arithmetical formula, but it's not necessarily the case when we consider, well, that's an evens, that's a serial. The answer, what's a serial property? It's just a sequence of arithmetical formulas, maybe with some, yeah. The common overkill approach is to do this with the universal quantifier. And we already saw that it doesn't work. Good. The instance probability, that's the natural thing to say. Then if you have a series, then it means that for each n, S proves fnth. Not bad, but it is not exactly what there are.
Because you can prove you might be able to prove every single element that you can enumerate, but you can't prove the whole series.
Yes.
The series is bigger than that. Okay.
Here's the here's the formal, here's the instance, the instance proof of consistency. The one which already everyone saw, including here. D be a formal derivation PA, since all formulas from D are true in the standard model, and the falsum is not true, the letter is not in D. The truth is it's invariant of the derivation, therefore the thing is true for each numeral n, hence provable in piano is a true primitive recursive statement. Because piano, you do. Yes, but the problem is that it's not a proof on PA, since the notion true in the standard model is not formalizable in PA. So you have to be careful. So in addition to instance probability of F and S, some sort of verification of 4 by means of the whole theory S is needed. And we're now entering the subject which was widely discussed. Hilbert clearly understood this, and it was widely discussed in the 60s and in discussion about the BHK proof for universal quantifiers. Surprisingly, that's how people. There are Brauer-Heiting, Kolmogorov semantics for intrinsic logic, and it was noticed that it didn't work in 2 occasions. It didn't work for implication, hence for negation, and didn't work for universal quantifier. Because for universal quantifier, what's the constructive proof for all x, f of x? We'll say, okay, there's an algorithm which for any x returns the proof of f of x. But then Kreisel was, growing older, I never actually respected him too much as a mathematician, but growing older, I respect him more and more. You know, he say that no, we need to have another proof that this procedure works for all inputs. Otherwise, it's you can do this kind of things and prove you know, the constructive proof of last Fermat theorem, because it's instance provable. And you don't have control about it.
If the domain of discourse is finite, then there's no problems.
Yes. Well.
I mean, with this BHK that you're just talking about. That's a good slide. With
yeah, I don't. Yeah, let me just provisionally agree with you saying. So instance probability doesn't work, and Hilbert was fuzzy about several things in foundations, in particular the most notoriously it's finitistic methods. What is finitistic methods? There are still discussions, but he was still rather specific about his effort to specifically prove consistency. And in particular, this is the summary from Richard Zah, who is probably one of the probably the leading expert now, the Hilbertist, how to say, in Hilbert studies. The Hilbert understanding of consistency proofs. What is required for consistency proof is an operation which, given a formal derivation, transforms such a derivation to one of special form. I didn't change a thing. And plus proofs that the operation in fact succeeds in every case, and the proof of special kind can be proof of inconsistency. The two-stage thing is obvious from here. In slightly generalized form, if we abstract from his epsilon substitution method, which didn't work and couldn't work by some non-Goedelian reasons, by some other reasons. Yes? Good. In slightly generalized form, the Hilbertian consistency proof is an operation which, given D, yields a proof that D is free of contradictions, and it doesn't prove a contradiction. The proof that I works for all inputs D. So this was a missing combination. In foundational discussion, it became clear in the beginning, in the early 1960s. Then we need this. It's called the second clause. You can check on Google the second clause for the BHK semantics, and it's Kreisel, and I praise him for this. Very good. And now the following definition represents approach in general setting selector proofs. And this is mathematical, what people don't quite understand, that was the, Roman Kozak quickly realized that we need selector proofs. And he said, well, but there is, if you take the honest proof that each, that consistent scheme is instance provable, then you can, mathematical proof, but you can extract the selector proof from this. There is a procedure which does, yes, but nobody did it explicitly, and nobody proved that the whole thing is provable in piano arithmetic. So this is a small thing, but important. So the proof of serial property, now there is a definition of serial property, I answer a question, is a pair of things. It's selector and verifier. Both are needed. And this pair is called selector proof. And now we'll play some easy examples that demonstrate that selector proofs have already been tacitly adopted by mathematicians. The time is right for logicians to catch up. Well, yes. Something wrong?
No, not something wrong, but whether...
just my student laughs at me. So
no, it's just because this footnote is my fault.
Okay.
This is entirely to placate me, but yeah.
Yes, please.
Yeah, here, I actually have a small question regarding this particular slide. I like this selector verifier structure, it makes sense, but here is one thing that I think we are omitting that is very important, which is that particularly the selector must terminate in finite steps, right? If a selector is allowed to continue on for infinitely many steps, then it's pointless. because that will trivialize everything. You could just run an infinite recursive selector, and then
You're completely right, but it was exactly meant there.
We're doing this in PA, right? So that means that our selector is going to be.
Yeah, yeah. There's the answer. Yes, it's the verifier does this. It says that selector. Well, when we go to this now, when we go the whole thing, you probably more trust the formal. Not the mathematical definition, but the formal definition. All right, formalizing selector proofs in PA, which the thing. So the serial property is syntactic parameter. Okay, the natural formalization. So an arithmetical term selector becomes an arithmetical term, which is the whole. And the PA formalization of the verifier means this one. PA proof that for all x, S of x is converges, of course, and there's a proof because if it doesn't converge, the truth predicate doesn't allow this. So it's built in, presupposed. And the BHK, let me see. Yeah, that's the examples I promised, but they're. Okay, BHK, I all told you. But consider BHK closed for all x. What is the constructive proof of the whole thing? In Kreisel's form, constructive proof is a pair, S and V, and the selector, as it was present in the first edition of the BHK semantics for this one. It says that for all x, yes, that fx is the proof of x, but we need a verifier. To prove that for all x, so there should be a verifier. So there are two things. The verifier too. That's actually where my ideas came from. That's how it works. Well, examples. Complete induction principle. That's the whole thing started to say that. This is a standard example from high school textbook for advanced kids. Well, not a textbook, but just entertaining math club for high school kids. So it's called complete induction principle. It says that the induction is not just from x to x plus 1, the usual, but we can do it, there are different other forms. In piano arithmetic, you can say that if for all x, if f psi of y holds for all y, less than x implies psi of x, then for all x. It's called the complete induction principle. Yeah, for ordinal people, it's more native even than the next plus 1. And the complete induction is provable by means of PA, and here's a textbook proof of complete induction. Apply the usual PA induction to the auxiliary formula for all y less than x, psi of y, and you'll get exactly this statement. And this is a selector proof. This because the thing is a serial property, where psi is a parameter of the serial property. And this proof actually for each given psi selects a derivation of complete induction corresponding to psi in a way that probably works for any input psi, because all this reduction is completely total and obviously converges. So its formalization in PI would we pick a natural primitive recursive selector S of x, which given psi computes the code of a derivation of PI of the whole thing, and find an easy proof in PA verifier that S of x works for all inputs, because it's so simple there's no way to make a mistake. And that's it. And without it, there's no, the complete induction cannot be represented by the single formula. So otherwise, if you do not allow, you shouldn't be claiming that complete induction is provable by means of in piano arithmetic. So mathematicians take it easily, yes. What about the product of polynomials as a polynomial? There's something more basic There's nothing more basic and nothing more obvious than this one. Yes? Given a pair of polynomials using the well-known formula, here's a standard mathematical proof. Given a pair of polynomials using the well-known formula, calculate coefficients of the product polynomial, P of f, g, and prove in arithmetic that f times g, that this time is a real product in piano, and this is the calculated coefficients. But this is a selector proofs. Because for each pair, f and g, they are not objects, they are meta-objects. They are not objects in, there are no variables of polynomials and that for each f and g, and this equality means that there is a derivation. It's not just equality of. It finds a proof of 6, and to formalize this proof, we built the grid recursive term product, which computes this product and computes the derivation of this, the standard derivation of the proof of this equality. And so this is another. It's a selector proof, but nobody doubts that the product of polynomials is a polynomial, and the whole thing is, of course, provable in piano arithmetic. Yes?
How do we justify that when we say it finds a proof of 6, this find procedure always works?
Oh, well, because it's a very specific thing. Because if you look how this P is defined, this calculate coefficients, and you prove the theorem, then for each see this yeah, or you do it by induction or by induction on everything becomes about Gödel numbers.
Yes.
And you prove by induction that it works for all f and g.
Yes, in this case we argue that when we say it finds, we can use induction to guarantee that it exists.
Yes, but what this induction does, it does exactly what it does. Yes. It says for each x and y, it finds the proof of this equality.
Yes, yes.
But it's a different proof each time.
Yes, yes. But this one, I think, yeah, I agree with you.
Yeah. Logicians. Are there any logicians in the room? How do you prove that double negation law in arithmetic, or any tautology which has variables? Because the tautology falsum implies falsum doesn't work as an example. How do you do this? Well, x is it's not a variable in piano arithmetic. What you can do, you prove that every instance of it is provable, but you want to prove it inside. So if you shape it properly, then you end up with perfectly nice selector proofs.
So, in a sense, I think what you're saying is, because PA is sort of first order-ish, anytime you want to actually say that there's anything that is a property of PA,
yeah, that
is just innate to PA, in a sense, you're always doing this because you can't just quantify the PA.
Absolutely, yes.
So
there's not
anything that's not an axiom in PA.
The whole meta-mathematics. The whole meta-mathematics is based on this.
Every induced axiom of PA outside of like whatever ground set you start with are all done this way secretly.
Absolutely.
And so therefore we should treat this like others. Okay. Yeah, that's a very strong way to put it.
Absolutely.
In other words, PA hat is you didn't invent PA hat, you just described PA hat. It's been there all along.
Yep. So I owe you one more very good example. But at this moment, it's a nice moment to say that, so selector proofs are everywhere. And in fact, then we have to accept this and study selector proofs as legitimate logic objects. In this case, the proof of PA consists within PA, which will follow very soon as a natural consequence. And if you don't accept selector proofs, we have to admit that such basic facts as induction, propositional tautologies, product of polynomials, and I follow your generalization and the whole meta-mathematics of first order arithmetic or something, they're not provable in arithmetic. Furthermore, consistency is not provable by the same bureaucratic reason. Selective proofs are not included.
So now we get to a question that I had starting out earlier that now we're ready for. And maybe you already anticipated the next slide. But is therefore PA plus selector proofs something that's a bit stronger than PA? And do we now have to prove PA plus selector proofs in PA plus selector proofs?
Yeah, it's yeah. There's also has been this question has been asked and answered. The answer is no. There's the selector proofs is just the compact way of proving things. But if you selector prove something, then it's instance provable. So there is no new, and the selector claim with the selector in is also provable in Piano. Mm-hmm. So we do not extend Piano. We
Selective proofs are elements of Piano.
Yeah, they live in Piano. We just haven't seen it. We saw them, but it's inside.
So PA hat is a conservative extension of PA.
Yeah. Well, that's provisionally because of to make it absolutely.
Well, one that is informal, one's formal, right?
Yeah, but it's well, that's my favorite, and this I immediately got from Moshe Vardi when I dropped him. I sent him the first version of this work, which was appeared as an archive preprint, and he immediately answered, "How can we do this?" Yes.
Yeah. So can we say that essentially to construct a selective proof, we need to establish some sort of chain structure within our collection of statements. And then following this chain structure, we kind of use induction to deal with selective proof and other kind of.
Well, it's a very informal description how Piano works. Everything is induction, yes, but it may be different sorts of induction and combined with some other things. I don't, yeah. Yes, there's a famous joke about Niels Bohr and Albert Einstein. And one of them was, Einstein was deterministic. And Niels Bohr was the statistical approach to things. And Einstein was sitting, and then each time Niels Bohr delivers a talk, Einstein says that God doesn't play dice. And Niels once said, Albert, would you please stop telling God what to do? So Piano has its own ways to prove things, and it's, but probably induction is clearly the universal thing. Now, so this is a Vardi thing here, and the question was, how can you explain this? And this is about the theory cannot prove its own consistency. Well, consider the theory that Conti is the standard consistency formula for any theory containing Piano arithmetic, and here's the sequence of theories. Piano, P0 is Piano, and then with each step you add the consistency formula. It's a standard thing which everybody does, and Goedel did, Turing did in the 30s thing. And PA omega, we don't need to go any further, is just a union of all the whole things. Here's a proof of folklore consistency proof Piano omega by means of Piano omega. Obvious proof. Let D be the derivation Piano omega, find n such that n is its derivation Pn. CompA, one of the postulates of P omega, implies that D doesn't contain falsum. Yes, case closed. The proof of consistency. Well, the proof of consistency by means of P omega. The answer was ready. Beautiful, Moshe. This is a beautiful, big and beautiful selector proof of consistency of P omega. Given D, you find the proof in P omega, then we find n and CompA and the proof that D doesn't contain falsum. Let me finish. On the other hand, by G2, P omega is a Gödelian theory. It's a primitive, it's a recursive set of axioms, and you can con PA omega. It's the formula built by Goedelian blueprint. But this derivation doesn't harm consistent proof above because the proof doesn't derive, this proof doesn't derive con PA omega. So it's clear that this is a good example when the Goedelian consistent formula deviates from the real problem of proving theory consistent.
So it's a folklore consistency proof of PA, but it's not a proof of con PA omega. Consider a folklore consistency proof of PA omega.
Oh yes, con PA. Typo. No, consistent proof of, sorry. Consistent proof of PA by means of PA. So, no, sorry, it's fine.
No, it's fine, but you're making a distinction between a consistency proof of PA omega in PA and a consistency proof of con PA omega, bottom line.
Oh, yes.
Exactly, yeah.
Because this is impossible, and this is impossible by Gödel theorem, and this is fine. And this is what the folklore proof, and Moshe asked me, can you explain how this thing corresponds to the Gödelian theorem? And this is a false populi. It's not I invented the whole thing. I got it.
So that proof in the middle of that slide is not a proof in PA omega?
No, it can be shaped. It's remember the selector proof. It's a proof, a mathematical proof which can be formalized in PA omega. So, but remember these two things. It's, if you wish, this is a proof in PA omega hat, but it's formalizable in PA omega as a selector proof.
I think I get the distinction.
Here I have one question. Yeah. So, if you look at this, isn't PA1 already too much? Because if you look at it, right, by definition, PA0 is already PA, and then PA1 should be PA0, which is PA, plus con PA0, which is just con PA.
Yes.
And then if we already have PA1, that's already PA plus con PA. And shouldn't that already be too strong?
The beauty of this example is that for each derivation d, there's an obvious proof that this d is consistent.
Yes.
And without any coding, you just take the Gödel number and you immediately calculate con PAN, which is where n is greater than the Gödel number of d, and that's it. That's why, in order to ensure this step, I'm taking omega steps in here. But from looking forward, PA is consistent, and its selector proves its own consistency, and each of them proves its own consistency. Selector proves its own consistency. But this is the most transparent and labor-free.
I have no doubt that the PA omega would prove its inconsistency.
Well, but then you just write a letter to Encyclopedia Britannica and then ask them to correct the one of their very prominent claims that theory T cannot prove its own consistency.
So your last paragraph just saying there is a P omega plus 1 and omega plus 2.
No, of course,
but each one I can then presume, maybe can I go on and then show they're also like
up to constructive ordinals. It's a separate thing, but it quickly becomes about numerations. So far it's about theories.
Sure.
But okay. Yeah, my question is, isn't PA omega too strong to begin with?
Too strong to be what?
To begin with. I mean, so
it was a question, and answer the question. Of course, we'll do everything for.
Make it some theory.
It's exactly as strong to be the theory that was asked about.
Yes, absolutely. But of course, we'll answer about PA itself.
Yeah, okay.
But surprisingly, the proof will be a mimic of this one. But
right.
instead of going to yet more and more powerful const statement, we'll do it through truth predicates, or for other things.
Just to answer him about being too strong, PA being too strong, can Pressburger arithmetic prove its own consistency?
Well, we need something. We need something. We need I sigma 1.
Formulate that.
Pressburg.
Yeah.
The coding on the writing the consistency.
With just plus equivalence decided.
Yeah, it's decided. Yeah, that's the plus. The Pressburger is decidable. Yes, and the formalized. Good question.
I'm guessing you can't even formulate a nice. There's probably no proof predicate, would be my assumption.
Yeah, that's the proof predicate.
It's inconsistent.
Yeah. Well, we'll think about it. Yes, but directly the whole story doesn't directly move because the proof predicate. We need to do this kind of reasoning.
Sorry, Dave.
Yes.
Can the substructural speak? It's a joke about Spivak. Never mind.
You're good.
You're going to have to explain it
One
to me
version.
later.
Okay, it's time for omega rule.
Yes.
Yes. Time for omega rule.
Okay.
Or this, what's the difference between selector proofs and omega rule? And thanks to one of, well, several of my readers who explained that. Of course, if you join PA with omega rule, it results in true arithmetic. We can prove any true arithmetical formula by unlimited use of omega rule. You understand how it is. It's infinite rule with infinite assumptions.
Hilbert would be angry with that.
Oh, yeah, absolutely, no. That's why in our response...
Mathematics.
Yeah, what selector proofs represent derivations of assumptions in a finite form. We just compactify saying that if the thing is regularly written, can be enumerated by some primitive recursive statement or some recursive sequence enumerations, then we can try to prove the whole thing inside piano, and sometimes we do, like consistency, but we never conclude this one because this one is too strong. So this is the selector proof area, and this is the consistency.
Yeah, got it.
I guess.
It's 8:30. Just how many more slides do you have?
Excuse me?
It's 8:30. How many more slides do you have?
Oh, no, just basically done, except that, yes.
Okay.
You're a family man, I understand, yes. me too, by the way, yes. Okay, so the selector proof consistency, the step 1 preliminary inspection. I'll finish. 3 minutes.
No, just go through the proof. Go through the slides so that we can put them on the internet.
Yeah, we provide a selector proof of piano, consistency of piano, and then formalize, and then we do it. Whether we assume the consistency of piano arithmetic, hat, no. When you reason inside theory, you don't assume the consistency of the theory, just reason. And it's a positive statement. You're not proving that something is unprovable. You're proving by delivering the proof. So it's without any assumptions or consistency. You may, somewhere on the way, you may end up with proving A and proving not A, but bad luck then, yes. And so we inspect with time, this thing's simplified quite a lot. In the sketch of the proof, inspect the well-known proof of reflexivity of piano. And it basically says that con PN be fragment of piano with the first n axiom, that's its notation. And then for each numeral n, PN proves con PN. If you limit the number of axioms in action, then you can prove the consistency of this fragment.
I remember from 5 years ago, he said the full recursion schema and truncated.
Yeah. So this truncated things, and this is, and then we're back on the Moshe example actually, because when you, from this proof extract a natural, that's important, which nobody, natural primitive recursive function, which given n builds a derivation of con PN piano arithmetic. You really have to understand how the proof works, and there's no non-primitive recursive steps there. Everything is simple combinatorics, which works. And then you have to to really just be careful. Note that convey implies G is not a proof of false one for any specific derivation G which fits inside this truncated fragment. And this is a Vardy style proof.
Typo.
You typo?
Contentual?
Yes.
That's right.
Yes, that's contentual means.
I think you meant contextual.
That's what this editor AI always suggests.
This is why math.
No, after 8:30 you're entitled. So this everybody is. Yeah, and by step one, and then we just end it. You find n, you take n, you find the truncated fragment n, which captures this one, and you conclude that it's consistent. And internalization, all this reasoning can be internalized in PA, and you'll get the desired verification of the selector. And this is by this Niels Bohr principle. I don't order this guy how to do, but you just it's a simple reasoning, which doesn't use any set standard models and nothing outside the simple combinatorics, which fits inside PI. And yeah. Okay. How far can we go proving consistency of piano? If piano can prove consistency of piano, but which was impossible, but maybe piano can prove consistency of something greater. For example, PA plus comp-PA, we call this standard PA. No, it doesn't. But still, you can make one step, and this guy, among others, notice that you can, piano can prove consistency of something stronger than piano. And this is a kind of a glimpse about the real Hilbert program. So it means how can we go on it? And the piano plus so-called slow consists of piano. Proof theorists know it. Yeah.
Here, a very subtle question. If we go back to a previous slide,
yes.
We assume D to be a derivation in PA, right?
Yes.
But then how could we make sure that there really exists a PAN such that D will become a derivation there?
So is it a question about PA hat?
PAN. So here, we define PAN, right? To be
Or on that, yeah.
We take derivation, yeah.
Truncated PA.
Truncated PA, and there is n, so take G, just the Gödel number of G. But the G is, when you formalize the whole thing in piano, then G is given by the Gödel number. There is no derivation, it's not an object in piano. It exists only as a Gödel number, so it's actually given. So this n is just given. Or given, not saying that that's well, no, I'm not.
There's a primitive recursive procedure.
The primitive procedure, which given Gödel number of D
You have to prove, you have to give a procedure that for any given Gödel.
Right, given any
that's
derivation D, there will exist an N such that every derivation proves it at some truncation level.
Yeah. So that's actually, it's a very good question, and I just suppressed it in there, but it's a legitimate question. Absolutely true.
Right.
And a good answer, yes.
Right, now every derivation will only actually need, won't need the whole induction scheme, it only need it up to N for some N for a given derivation.
Right, for sure.
That's all he's saying.
Yes.
Yeah.
So we can.
The box finally shows up.
Yeah, that's true.
Every slide had a box on it.
Yeah, that's great.
Wait until almost 2 hours in talk to see the first box.
Absolutely. So you cannot make big steps, but slow steps you still can go. And it's a question how far in this direction you can go. What was wrong in the first argument? So that's a good point. Gödel theorem, Hilbert consistency program. There's one one human story, and then we'll end. Norton, thank you for your incredible patience and hospitality. But it's an amazing story. Kripke in 2022, it was his actually the last published paper, and actually, well, except as usual, he do it gradually. He announced it and spoke in some ISL meeting. It appeared as an abstract somewhere, and then the complete text is there. It's a BSL, as I remember, and it shows that Hilbert epsilon substitution method was not succeeded by non-Goedelian reasons. But if you look at this definition, then assumption that all this phony justification for unprovability of consistency assumes that whenever whatever potential proof of consistency would yield conp-A, then you cannot prove conp-A, hence it cannot. But if there is nothing in the epsilon epsilon substitution method which hints that it should be if successful, it should produce a statement which yields conp-A. There's nothing there, and so when you look at my method, on the selective proof method, it's a proper the little generalization or modification of Hilbert epsilon substitution. We don't do this epsilon substitution; we do it in a more general form, and use some powerful meta theorems which are not available for Hilbert at the moment. So there's no justification. There has never been justification for UCT, and the substitution method, epsilon substitution method, Hilbert epsilon, fails for non-Goedelian reasons. That was a separate reasoning by Sol Kripke. He gave this talk, and probably Norton might remember it. I heard this too. So up to 22, the Hess was unfairly treated. Sent to Venezuelan prisons without proper authorization. All right, we're not claiming it back because it doesn't work actually, but for non-Goedelian reasons. But it's surprising that the misconception, the wrong pill existed for so many years. And some proof theory, and this will be a subject of the talk, but this, to answer this proposition 2, if you look at the proposition 2.2, probable in piano means selector probable in piano yields instance probable in piano. It means that you never leave the confinements of the piano. Neither in selector proof nor in concluding that all these instances are also, each of these instances is also probable. And now I cannot, sense of piano, okay. What about ZF?
I was going to ask you, there's two proofs of the consistency of PA, Gensen. So you're doing what Gensen's.
Well, he had his Gensen had a bunch of ordinals in there. I didn't see.
Right.
The only ordinals I saw here were less than omega.
Right.
The ordinal on top was omega.
So we're going to talk about ZFC.
Yeah.
Do you want me to take that? Because you use the true predicates here, but you can also do this with the sort of Gensen style ordinals. But it's a similar.
We can do the smaller ordinals and cook up the selector proofs from this one. So this the Gensen's proof also yields the selector proof of consistency, but of course not the conclusion, but the procedure. Moreover, it's half of the procedure says that up to epsilon 0 suffices to do the whole induction, but you can formalize inside piano, which was the cornerstone of all these ordinal analysis. Any induction to any ordinal which is less than epsilon 0 is formalizable in piano. And this part suffices to cook up the selector proof. So it's a totally different approach. And this was accomplished by this gentleman who also speaks in in New Mexico. Now ZF.
Is that just to sum up?
Yeah.
Jensen's methods are more powerful than yours.
Because it gives us, it proves something which is outside piano, yes.
Okay.
But the problem is not to be powerful, but in order to be, to do with, it's like you're doing some construction by compass and ruler, but the point, you do it with limited means. All right, so ZF can prove its own consistency the same way. Because it's reflexive, it does all the whole things. All these reduction procedures are primitive recursive. You can cook up the selector proof. But the reasoning, but what's the point? And the point is that whether mathematics is able to prove its own consistency, the answer is yes, but you can prove the consistency of ZF and ZF, but then do you trust ZF itself at the first place? That's the point.
Couldn't you trust it a lot less?
Yeah, if you trust a lot less, and this is a key of the Hilbert program. But, well, apparently this particular method gives you some inch. You inch forwards, but not too much. But there might be some other ideas.
I mean, the barrier anyway, I was thinking about is, for example, what I would like to have, and I think what you just showed me means we can't have it, is, real Hilbert program would be like, I would like to prove MLTT consistent by means of PA, but I think MLTT can prove COM-PA, so that's right out. Right?
That's right, yeah, that's true. Yep.
Or else you may need to conform with that.
Yeah, and I don't
So the universe is actually distorted by Gödel's theorem, but not the naive way it was thought of. Yes?
So if we want to generalize this reflective selector proof into ZF, if I'm correct, we need some sort of transfinite induction step to replace the original induction step, right?
The reflexivity, essential reflexivity of ZF. Of course, it uses some models and some reasoning, but it boils down to describing the selector. Still, at the end of the day, using all the things which are formalizable in ZF, you can, given phi, you can give the proof of conphi in ZF.
Unless we could somehow build ZF with a countably many sub-theories, which I believe that it will be either impossible or very hard to do. But unless we can do that, then we need some sort of transfinite inductions. But is this transfinite induction steps included in ZF?
The problem is that it's about added value. If you trust in ZF, then you can prove the consistency of ZF. But the higher you go, since it's the same theory T you're proving the consistency in, then the more trust you have to put in the so-called trusted core. So and that's the mathematical value of the whole thing diminishes.
Right. So it's very close. So what Goedel's theorem told us is very close in a sense to what it tells us, because it places all of these very structural limits on how much you can go up before you're proving con.
Yep, that's true. Yeah. That's true. Absolutely, yes. That's still
sedimented.
Yes, let the minds over.
Right. But then, of course, you can ask different things with different levels,
Well, maybe there are ways around things.
Others, so,
yep. At least there is some reasonable area to think, and that's basically it. Okay. Any progress on Hilbert program? That's what we discussed. We basically abolished, they eliminated the probability of consistency thesis, at least in its Encyclopedia Britannica version, that it can be formalized. Of course it can. And the second completeness theorem does the job, but not the straightforward way it was thought to be, and the Gilbert consistency program was not completely dead because of this. There are some ways to move, and we need new ideas. With this, during these 5 years, we basically exhausted. We try the way, and we have done now. We deliver the structure of the world. You cannot make steps which was thought impossible, but still some limited way. And each step is a labor. And yes.
Okay, at the beginning of the talk, you mentioned, after 5 years, you have this written up.
Yes.
So I was wondering where to look to get a copy of the write-up. Now that I listened to your talk, it's I can read more detail.
Basically, the math is written and published, and it was recently, past summer, it was posted on the Journal of Logic and Computation, Oxford, and quite recently, a couple of weeks ago, it was assigned the volume and the number. And if you just...
I look up for, I'm sure if I look it online, I could look.
Yeah.
And maybe when you put the slides online, if you just don't,
yeah.
Oh, but I got the references slides. So
the reference slide is absolutely.
I'll just look there. Okay, great.
And one of the principal contributors, Ella, is here, yes. Thank you. Nelson, I owe you beer if you take it. So,
Well, I think more questions? We can still pester. We pestered you a lot.
Yeah, no, this is great. Good luck knocking that at the top. Convince everybody.
I think a suggestion, maybe like when you give that talk, make a 10 minutes break after 1 hour.
I understand. It's like philosophers do. And then the talk after a while. So it's okay. I understand. But
How long is your slot to speak?
It's 1 hour talk. Of course I will be much less generous with comments. But people will get less.